Okay, so I think we are ready right now. So at least we have all the presentation. We are live on YouTube. So for the people who are presenting, so please don't move further than that. So that's why you have the big sign behind me, and you can stay over there. Otherwise, the people who are online will not see you, except if you want to hide. So you can move out of the broadcasting zone. That's fine. Okay, so welcome for this last session, last effort for concluding the week, almost. We have the 12 presentation. We are supposed to go and to have 15 minutes shortly. We have already lost 20 minutes as usual, so not really surprising. Everyone is there from the different universities, partners, and so on. Once again, all computers disappeared. Yes, thank you. It's better. Now everything is done. For those who have still not uploaded the report, the engineering report, I think it was obvious that it was supposed to be finished for today at 9. Otherwise, for sure, you will continue to work after 9 today because you do not have any computers, so of course. Okay, but for those who have not uploaded the report yet, you can do it up to tomorrow morning. So if you want to spend the night for updating the report and so on, so you're welcome. I think we can start right now. We will start with the team number 5. Not because it's the first topic to cover, but they have some logistic constraints, so we will start with them right now. So the team number 5, please. We will do all the presentation this morning and this afternoon. We will keep all the videos for this afternoon, and obviously we will play all the videos all together. So that's good. I mentioned no behind the back. So it means so don't. Not behind the back. You have to be in front. We just see half of the video. As you know, we only have 15 minutes for the presentation, so I will show you if you have the 15 minutes. Then you have to be faster to finish your presentation, okay? Good morning, everybody. The subject of this presentation that should give to us this week is the following: full plane representation and accuracy of processes 1D, 2D. To begin answering our questions, we began by defining the term in our questions. The full plane. The full plane is the area surrounding the river that is subject to flooding during high discharges. It is therefore necessary to understand how water circulates in this region, and it is important to model the flow of water here and this area of exploiting with building and agriculture. The accuracy of processes we define as being independent of the type of model used, 1D and 2D model. We must therefore produce an output of
of 1D and 2D models and compare their ability to model the full plane. We choose the 2011 event as there was a large amount of data available, and it is more recent than 1994, with no issue of much failure. In order to meet our aim, we identify more aim objectives, compare 1D and 2D models processes for the full plane, and find the limitation of processes represented. For it, we split the group into 3 parts. One constitutes the theoretical processes for 1D and 2D models. Another group to produce output for equals, and another to produce output for telematic. We will then work together to compare results between our models and to the theoretical findings.
And I would like to explain to you the difference between 1D and 2D models. Both 1D and 2D models are based on the mathematical quadratic equations. In 1D models, many cross-sections are taken and which describe the available value in the system and the slope of the channel bed and the roughness. In 1D models, it is different that is based on the assumption that the flow is one-dimensional. The meaning is that the velocity and water levels are uniform across the cross-section. With 2D models, the terrain is represented as the continuous surface.
So, to start with the modeling, we first defined our domain. So, we are modeling the lower part of the river basin, starting from another ridge, since there is observed discharges available. And for the downstream, we extend the domain up to the Mediterranean Sea, just to represent better the lower part that is near the airport. To start talking about the topographical representation, it's important always to first check the DEM that it's going to be used. And we can see in the left side that since the resolution of the DEM is 5 meters, also the bridges are represented. So first of all, we need to process the DEM to extract the information of the bridges, at least in the river bed. And that's what we have done, seen in the picture in the right. And for the representation of the winds, since the resolution of the DEM and it's high, as we can see, they are represented in the topography, and we use that for the modeling. Now, why I chose HGRAS? So basically, HGRAS has the ability to define a position of the levee that will constrain the flow of water before the water level reaches the height of the levee. As my colleagues explained before, with a 1D model, we only can represent one uniform water level in the full cross section, so that's represented in the picture in the left. By using HGRAS, it's possible to deal with this constraint. Just to show an example with a different software, in 911 it's not possible to define these limits to constrain the flow, but a different approach can be used. This is known as a quasi-2D approach, where you define different branches for the river, which is the upper one. And in this example, there is just one branch for the floodplain in the lower part. So to link these branches, use of link channels is done. In this way, water can communicate between the two different branches. But since this is a quasi-2D approach, we chose to go for the HGRAS. Yeah. So to start with setting up the model in HEC-RAS, we first need to extract the cross-sections. For this, HEC-RAS is used, and in this tool we extracted many cross-sections. All of them are separated by a distance of 100 meters, and our domain covers around 15 kilometers length. In the same way, by using a satellite image, we have assigned different values for the roughness in the riverbed and also in the floodplains, as you can see in the table. All the values were taken from literature and tables available. And this is the hydroeurope that is being used as upstream boundary conditions for the simulations. As I told already, the hydrograph in the Amanda Bridge is the upstream boundary condition, and for the downstream boundary, we obtained a rating curve based on many equations, assuming rectangular cross-section at the last cross-section of the domain, just to obtain the rating curve. And the initial conditions, it's a constant discharge value of 20 cubic meters per second. That we chose this value because by looking at the hydrograph, this was the initial values of our simulation period. To check the stability of the simulation, the grand number is used. So in this way, we can set a time step that gives us results without instabilities. By doing the calculations with 100 meters length between the cross-sections and an average velocity of 2 meters per second, the minimum time step that is needed is 50 seconds. But in our case, we use 30 seconds, and then we have 17 days of computations and output each 30 minutes. I forgot to mention that in addition to the model with cross-sections each 100 meters, which is shown in the right side, we also interpolate cross-sections to see how different can be the representation of water levels because of this increase in cross-sections. For the case on the left, we have to reduce the time step to 1 second, and you can clearly see the differences in the representation and how the cross-sections are interpolated and the changes in the topography, how they are represented. Finally, just to show the differences or the impact of the increase in cross-sections, we have plotted these two graphs at fixed cross-sections, where we can see that there is a slight variation in water levels due to the increase in cross-sections, and for the discharges, it's basically the same. There's no impact.
So to build up a model, we use the same area of AquaCloud. We use a 25 meter size mesh, and we add some part of the sea buildings. For the building, we chose to only add the building with a narrow area in superior at 2,500 square meters, and we try to remove bridges elevation. For the variety simulation, we use two boundary conditions. For the upstream, we have an upper we prescribe discharge, and for the downstream boundary, we use upper boundary with prescribed water level. We use several finite elements from numerical scheme. We chose it because it was the fastest to compute our simulation. And like for HRAS, we use the manual friction law. we try to do a distribution of the money along our domain. With Denmark, we obtain debatable results. We find the false few observers. We still have British impacts, and the mesh size and that state was too high. But we cannot do under because we cannot compute. The simulation was too long. And we also face the children's problem. Like you can see on the picture with the velocity. This is a fruit map that's presented here. We have a quadruplet calculated, and we can see that the bridge disturbed our flow, and so the fruit plane are not well represented. And on the other side of the slide, you can see a zoom of the airport zone. And you can see the building and the water pass surround the building. This is the same map, but with the velocity distribution. And you can see at the upstream near the weir that we have higher velocity, and it's because of the turbulent flow. Thank you.
In conclusion, we think 2D models are more accurate as they are able to account for variability in velocity and water levels. Both model accuracy can be improved in 1D model. We can increase the number of cross sections. However, this will increase computation time. In 2D model, we can create a finer mesh. Our results suggest that Telemark is better representing the fruit plane in terms of accuracy of processes. However, the main issue is that we don't know the purpose of the 2D. If the purpose is food forecasting, then we need rapid data, so 1D may be better. If we want to design the fruit plane, then we need accurate results, so 2D may be better. Thank you for your attention.
Thank you. So no red flag regarding the time. So we have the time for questions. Yes.
Thank you for your presentation. It was quite nice. Can you go page 4? So it is for the model description, 1D and 2D. So you wrote that 1D is better for low gradients. Which variable? The topographic slope. Why?
When the topography is relatively uniform, it will be enough just to use 1D model because we will not have too much irregularities in the topography. So by having one uniform water level, the representation will be enough.
Okay. Okay. You say that you tried in Telemark to remove the bridge. That's it, but you failed. You know why or no?
Yeah. Since the time that we have to work is limited, more work was required. We failed at removing some parts of the topography. So at the end, there was still some points that were representing the
Okay, and if you succeeded, you think that you have to remove something somewhere else?
Yes, especially with the bridges, not only in the river, but also in the floodplain.
Okay.
Yes.
just one question, yes, because you said you choose 2011 the flag, okay, which is have better database or something. But do you have more knowledge about this, and do you familiar with this flag? Because, for example, you have more data, but it's also because you are an engineer, you need to know that this flooded, how it losses or something. Do you have some knowledge of this? Because in your technical simulation, we know that in 2011 the airport is not flooded, but there's water everywhere in your airport. Have you noticed this?
Yeah, we know that our 2D simulation was totally false because we have, yeah, it's true, we have a time step of, I think it's 20 seconds, and our mesh in 25
Okay, anyway, but when you, I mean, my point is like just one comment. When you choose to simulate any flood, the data collection is important for sure, but you also need to understand, you need to have some effect of your results.
Yeah, the flood of 1945 was not very well measured, so we chose one well measured.
Okay.
Okay. So I understand you had the flooding, but I think the flooding was not due to the time step. I think this is a problem in the geometry, which is generating the fact that you have the flood which is going on the left bank. I think that's the problem you mentioned about the shape of the structures. Any additional questions? Oh, that's fine for everyone. Yes? Okay. Thank you very much. So now we move to team number 8, please.
Yes, because yes.
Hello, we are Team 8. After hard working during this week, now we are going to present our second questions. Details on the modeling methodologies for the 1994 flood event in the Var Valley. So our presentation consists of the 3 parts. The first part is to give the general methodologies, and the second and third parts focus on details. The first, general methodologies. As you've seen in the flow chart, there are 6 steps. You may notice that there are 2 important loops. First one is the data treatment, go to the data collection. And the second one is the validation, go through the model setup to the post-processing.
So here we're going to talk about the details of hydrological modeling. The aim objective of the hydrologic model is to get a suitable hydrograph for our hydrologic model. So for that, this week we changed a little our hydrological model by creating a new subcatchment at the lower graph. So as we can see on the map, the first subcatchment corresponds to the Lamella Bridge outlet, and the second one corresponds to the airport outlet. So here in the table we can see the parameter that we use in our hydrogen model. For this parameter, we look for method to calculate them more adapted to this case study. So, for example, for the time of concentration, we use the Gandhi method that's a method adapted to mountainous basins and commonly used in Europe and mainly in Italy. For the transfer method, we use the SCS unit hydrograph. It's the most common and known method, and also adapted because it's adapted to our available data. For this loss method, we calculate our curve number and the unperimeability with ArcGIS tools, and that with the land used to calculate it. For the curve number, when we calculated it, we consider the soil as wet. So for this case study, we modified it while keeping reliable values. So here in the table, we can see the values that we use for our hydrological model, and we can view also the two subcatchments that we create with ridges and junctions in the model. Here we have the hydrograph at the Lamella Bridge outlet. So we can see the peak of this discharge, and as we expected, the time of peak is 5 p.m. And it was before the one of the Napoleon Bridge outlet. This hydrograph, this is the hydrograph that we can use for the hydraulic model.
Okay, for the hydraulic model, we are considering the hydrograph for 1994 and Amanda Bridge, and as this is changing over time, then we have to consider a 5-flow instead for an steady flow, to consider the change over time, and we have to consider the geometry, the moderate conditions, initial condition analysis, internal structures, and the stability of the model for the unsteady flow conditions. Then, for the geometry, we have to find a good geometry that represents well the channel and the floodplain. We process the information in the data treatment to find the best way and the possible errors that we can find in the topography. And we corrected the topography according to what we expected of the flood and according to the real domain of the real domain that we're analyzing, that is from Lamanda Ridge to the sea. We chose Lamanda Ridge mainly because it's a control point. There is a ridge there, so we expect that the section of the bridge is not going to change too much over time, and the sea because we will try to avoid some errors in the definition of the domain after model condition. The topography we used was of 2009. This topography was taken after the collapse of the two wells, so they are not considered. If they want to be considered, the topography must be changed or according to the condition at that time. That is very difficult to consider. And the regions were considered domain. And the mesh domain that we use is the one shown at the right. For the model conditions, as I said before, we use Lamanda Ridge with the results of HMS calibrated, and for the downstream part, we use zero level of water at the sea boundary condition, and initial condition of zero also, and to avoid sea effect of the bridges and the mouth of the river. For the initial condition and land use, for the land use, we use assignation of land use according to what we are going to see with the Google Earth map. We didn't have any land use to assign, but it was more or less clear to find different characteristics in the land use according to these areas. So they were characterized according to the condition we found. And the values given are the ones shown there, and are the ones by default by user that have been verified, and we didn't have any way to calibrate them as there was no more information to this process. And for the initial condition, we decided to do a warm-up time. The warm-up time was with 300 kilometers per second at the boundary condition of the upper part. Due to it was better to fill the channel without creating wave effects or flooding areas with an initial condition layer that may be dry during that period. For the internal structures, like the main information we had was the information of the buildings and the connection between intersections. It also depends on the availability of the information, which information we can represent. The topography, the words were already represented, and you can represent any type of information. The buildings, words, gates, walls, bridges, and its intersections. Anything you can try to think, you can see. And this is one of the most important parts in the setup of the model that sometimes is forgotten, like the model stability. For the model stability, it is necessary to choose, depending on the model, a time step or a current coefficient, that is the CFL number. It depends on the type of scheme. For example, if you use an implicit scheme, it is always stable. It is less accurate because you can decrease the time step to make it less accurate but faster. So it can have weird information results, but then you are going to have a quick model. And for example, for the case of fever, like explicit scheme, the CFL number is fixed. You define it at the beginning, and the time step changes according to a property in the section. According to the equation shown below, that takes the minimum value of the time step for that time step calculated. And it also, if the DS, that is the phase of the mesh, is very small, then the time step is going to decrease a lot. It's going to make a longer time calculation, but it's going to be more accurate in some areas. And it's like a fight. Like you have to decide between you want to have accuracy or you want to have a good processing time in the frame of the model you use. And you have to optimize this parameter because you don't want to have a model of 3 months, but also you want to have an accurate model. So there are different conditions that you can have. If you use 1D, 2D, or 3D, it's more or less the same. That you have to reduce the number of elements in the domain. Sections or surfaces, you have to increase the size of distances in the relevant areas. Like for example, if you know that the sea is not going to change too much over time, or if the upper part is less important for you, then you can give a higher mesh size. And you can give a smaller mesh size to the areas below, so you improve the calculation time. And you have to be careful with the selection of the domain, because of course, if you select the mountains and the mountains are going to be dry, they are also going to have weight on the calculation. It's going to make the model slower. So you would have to select a smaller mesh that you are sure is not going to be outside the flooding area too much, but it's also not going to cut parts that are going to be flooded. And for the mesh we used was a mesh varying from 8 meters to 300 meters according to the importance of the area. And the mesh we used for the final simulation was the one shown at the right. And to choose the model, it's basically these steps are really aligned for all the models, which are similar, but they can be also used for Grass, for Telemac, for Mike, for fluvial floods in this case. There are 4 questions that are important to consider at the moment. Like, what is the most suitable model is 1D, 2D, or a hybrid model. For this model, for example, it was better to use a hybrid model, but due to time, it was difficult to implement, and we used the two fully implemented model. Is the model effective to represent the desired information or the desired features? Like, for example, if we want to represent one intersection between streets, like some models cannot do this easily, some models can do it easily. Is it feasible to complete the task in the given time? Like, of course, it's going to be difficult if you choose one model that has a very long time of calculation, so you can improve that, but also if the setup takes a very long time, it's almost the same as having a very long time of calculation and IC setup. And is the user competent to represent the desired features with the chosen domain? This is like one of the most people wants to ask, because of course the company doesn't want to tell you, and you can decide which model you are going to use. They are going to tell you have to choose this model. But of course, if you are not able to represent it, it's going to be very difficult for you to try to make it time. These are the final results of the model we designed. Like the general illustration of the flood map with a zoom and the big scale. The two map have the same depth scale. And then the one on the right has a more detailed mesh color to see the differences in different areas of the flood area, mainly in the city, because it's the main important location. Now we want to know really the conditions in the area. But to know if the model was good or not, we have to compare qualitatively. And this was done comparing information in Napoleon during the flood of 1994. Like the real representative value that we consider to represent the 1994 flood was the depth, because it was the measurement. So we took 3 points, 3 reference points on the bridge that were flooded, and we compared it with the observed measurements in Napoleon bridge. And the results, for example, for the point 3, like the deepest one, that the calculation is given by the deepest point, so it should be very similar. They show that the peak is very similar, even though it is a little displaced and the time of calculation was very long, so we just made a little longer of the peak.
So far we have been able to achieve a good model setup and good results. The methodology we applied revealed a successful HMS and ADO models. The VAR attachment the model represented similar flooding that was observed on the ground level. Results showed a delighted representation of hydrographs and inundated areas. And the water depth at Napoleon Bridge obtained using IDOT showed similar maximum depth that were observed in the original unit. So this is kind of a conclusion that can emphasize our setup of model. And all the points that Andres has mentioned, if we take it into consideration during setting up a model, we can achieve a close model towards the observed value. Thank you.
Doing the search of the video. Any question?
No question, but comment. I think that you are answering the questions for the hydroeurope part and not for the hydrological part, because the question was about methodology, and you were more presenting concerning hydrology, what you've done with HMS and not a general point of view on hydrological model. No, I don't need the answer because this is just more remark. And one point for hydraulic modeling, we discovered that you have used either only
point of confusion. You're presenting a lot of things, you're wondering which tool you are using, and you don't know.
I have a couple of questions and a couple of remarks, maybe the first question is more on your application. You showed on the slide 17, you showed the comparison of water depth from observed data and simulated data. Is it really water depth or the water level?
Water depth.
Okay, so if you do you have a slide with DL data? So basically, what I want to say is the bridges was removed, and the bed level in the place where it was removed doesn't make any sense. So it's not interesting to comparing water depth. It's really doesn't make any sense. What you should compare is water level. Okay. Because the bed is completely wrong. Okay? Do you see what I mean? It's just like some reservoir or whatever.
Well, there is no wrong. It's not flat. It's representing the.
Yeah, but water depth is the difference between water level and topography, and topography is completely wrong, and you know that it's completely wrong.
It is not so wrong. It's just that it's representing the slope in the bridge. The only problem that is wrong is because there is no representation of the bridge and with the pipes.
But I think if you look at the DM, you see that in the place the word of bridge, there's clearly some constant topography which doesn't necessarily fit interpolate the update. So if you look at DM, you will see that it's not, it is artificial data.
It's artificial, but it's not wrong.
This is your opinion. And another point, if speaking with us will be on DM again, could you show again the flooding simulation? So this is a 1994 event, and the airport is flooded. So just look by which part it is flooded. And I believe you are using modern DM. So I think that if you try to simulate 2011 Everett, you will also flood the airport. And the reason why is that the DM does not represent leads. So this is more a remark, but if you look on the DM, again, there is a part where the leads are missing, and again, it's next to the bridges.
That's the reason we said in the internal condition that it's not available. We cannot guess where it is stuck.
So
here, there's no recourse. Like they can be added in the model depending on the information available. We cannot get the information in there if we don't know exactly if it is there or not. Like, or if we don't have the information. So it depends on what we have. Yeah, because we know that the bridge, the wall must not be there.
Here it's also bridge, but we don't know.
Which bridge?
Yeah, we show it here, and the flat map is, it definitely didn't show this channel.
You mean those?
Yes, if you remove these three parts.
It depends how you represent it. In our case, we represent this as a sink and a source. You are sinking the water in one part and sourcing it in the other part. As representation of the connection between the intersections, they are represented. If you see, for example, in the video, you see here the water in the upper part of the intersection is coming to the lower part of the intersection as a source. They are represented.
thank you.
Thank you very much. Question number 10, please.
Hello, we are Team 10. I'm going to present to you the work we've got up to this week. So this is what will be the outline of our presentation today. So our aim this week was to simulate a 300-year return period event and compare it with the 1994 event using flood extent water data. So to do this, we collected data from France, the discharge data, and then from this we developed the 300-year return period using a number distribution and a rescaling factor to develop our hydrographs, and then these were input into either along with other background information.
So I'm going to talk about the method we use to obtain the hydrograph for 300 years return period. Sorry. Okay. So last week we used the local synthetic formula to obtain the design zone for different return periods, and then we used HMS to obtain the hydrograph. But we were lack of information for the specific coefficients for different subcatchments. So that was a limitation of that approach. So this week we use another approach. We use a frequency analysis by Gumbel distribution. So firstly, we need annual peak discharge. It was the first problem we faced because the data we have was a historical daily discharge, and by using that data, we calculated the peak discharge for 300 years return period, and that was even lower than 1994 event. So that was not right. The reason could be the daily discharge was an average value, or it could be a measurement at a fixed time for each day. So it actually didn't catch the peak value. So for that, we collect the data from the website, People, and we found the hourly discharge from 1985 to 2000, because we could get a continuously recorded data. And the observation point we chose was Napoleon Free Bridge, and by the hourly discharge, so we could catch the real peak value. And then we use the Gumbel distribution and extrapolate the peak discharge for 300 years return period. So here you can see the cumulative frequency analysis on the graph. So the calculated cumulative distribution function was the red line, and the observed data was the dots. The X, you can see the discharge, and the Y is the probability of non-incidence. So it helps us to know how likely the flood event is going to happen in the future again, based on how they happened in the past. So here we plot the peak discharge against return periods. By extrapolating the graph curve, the peak discharge for 300 years return period was obtained, and we got was 4,465 cubic meters per second.
Now, on this part, I'm speaking about how we get the hydrograph for a return period of 300 years. So from the analysis of the Gumbel distribution, we obtained the peak discharge, which was about 4,500 cubic meters per second. We consider that the dynamic of the flood event of 1994 is similar to the event of the return period of 300 years. We determined the rescaling factor, which is which is the ratio between the peak discharge of the return period of an event of a return period of 300 years, divided by the peak discharge of the 1994 event. And with this coefficient, we multiplied it by the discharge of the 1994 event to obtain the corresponding discharge, and so the hydrograph of the return period of 300 years.
So we run our simulation with the Eber software. So we put the input and output. So for both simulation, we put downstream boundary condition to 0.2 meters of elevation. We put an initial condition in the riverbed of 0.5 meters. For the roughness, we use the land layer on which area was affected from mining coefficient. We use a 5.5 meters DTM. Which we combine to a building layer, and this building layer we settle all the elevation of all the buildings to 10 meters in order to have a proper elevation layer. With the time interval of the first simulation from the 1994 we use 60 hundred seconds, and for the 300 years we use 1,200 seconds. So here you can see the implementation of the mesh for the 1994 simulation. So of course, the areas that were willing to be flooded, we put a more precise mesh. So for the industrial and residential area, we put 8 meters of mesh, and for the river, we put 15. On the left part, on the right part, you can see the land use layer. So we can see a huge area of brushland in the middle part of the river. As we settled the 1994 flood simulation before the 300 years simulation, we reduce our study area for the 300 years simulation in order to have simulation time, to have a quicker simulation time. So as you can see, the industrial area and residential area have the same mesh, but the mesh is less important than during the 1994 simulation. On the right part, you can see the curve, because we put curve in order because the DM wasn't taking into account the fact that the water could flow below here the highway. So we set those several of 5 curves. Also, in the DTM, we deleted the bridges in order to let it flow past in the level.
So with the Eber software, we did two simulations. One for the flood of 94, and the other one for the flood of 300 years return period. So the first one is for 94, so we can see the flow going from upstream to downstream, and we calculated the time taken by the discharge to, well, at the point we put it inside the model, and the time the peak discharge reaches the outlet boundary condition was 1 hour and 28 minutes. And for the 300 years reasoning period, the time was a bit faster. Well, it was 1 hour and 20 minutes, so it's almost the same, but the velocity of water was increased for the 300-year return period compared to the 94 years. So here we have a comparison of the two events. On the event for the 300-year return period, we can see on the legend that for the peak discharge, the water depth reached 1 meter over the maximum water depth is almost at 1 meter over the maximum water depth for the 94 event. And also the extension of the flood area is more important, especially on the right upper part, where are some industrial areas located, and also there are some downstream, some brushes. Also for the elevation at the Napoleon Free Bridge, just upstream the Napoleon Free Bridge, the water depth around the building of the administration of Nice, the water depth is more important for the 300-year recent period than the 1994 flood. And also we did some measurements and we observed that the water depth was about 3 meters for the 94 event, and for the 300 years event was almost at 4.5 meters depth.
So reflection and all the things that are important in order to have a proper simulation. So the importance of the downstream boundary condition. So we put the boundary condition far from the outlet, but we didn't do that in previous week. So to put the water elevation in the downstream condition. The fact of progressive decreasing the study of area is important because we have a less important simulation time. It was really important that the 1994 simulation take a long time, and we didn't have much time to do the 300-year simulation. So we needed to decrease the study of area. And as was said previously, we have a potential danger for industrial, residential, cultivation, and of course the airports. So our recommendation. So first we could set up an afforestation in the riverbed, in the middle part of the river, in order to increase the water level and perhaps create some artificial flooded area in the brushland in order to decrease the downstream quantity of water that will flow. We can also improve all the protection equipment, like construction of levee, dikes, firewall. One of the solutions could be to delete all the weirs, or at least one of the upstream part of weirs, in order to prevent the upstream water elevation. Because in the upstream part, we saw several areas were flooded, and it was corresponding to the area where the weirs were settled. So one of the solutions could be to delete at least the upstream part weirs, even if we know that it will create a huge density of water in the middle and downstream parts.
So the biggest limitation of our study was the lack of data, because the Gumball distribution requires you to match your fit to the data set, and we only had 16 data sets to try and match the 300-year return period to. But overall, from this week and last week, we have presented different ways in which to produce hydrographs different return periods. But overall, it's very dependent on the context they're needed in, so need for resilience, and it's also dependent on the data available. But from looking at 300-year return period compared to 94 event, we can work out how to reverse the this method to deal with a large flood and also hence in small floods. Thank you for listening.
Questions? Yes.
Could you please go to the slide number 12? And anyway, thank you for a very nice presentation. So could you give you passed out, well, let's talk, sorry. What is it? I don't know either. What does the color means? It's mesh size. So I have a very little remark. It's not my question. It's not about this, but you see that the slide on top and the slide on the bottom, the color code is not the same. So it's kind of hard to compare.
You just need to see the legend.
Yeah, but it should be nice if it would be same. It would be much easier for me. So is it what happens with the mesh? So basically, my question is why you are not using the same mesh for two pieces?
This is the same mesh.
It is just that
we reduce the study area. Because we know that in the mountains there will not be flooded. So we reduce the study area.
So both simulations are made on the same mesh.
The same mesh.
Okay. Thank you very much.
We just for the 200-year region period, We don't see well on the screen, but on the downstream part, along the river, we set a mesh of 5 meters in order to have more precision to see what's happening along the river to have better observation of the overflow from the river to the urban area.
I have a question of clarification on slide 11. Just to look back, you had a scaling, or maybe it's 10, scaling thing. I wasn't quite clear why you actually did this. Was it just to show what the scale difference was, or was there some point to this?
Sorry, can you repeat the question?
Why did you work out a scaling factor? What was the point of doing that?
Actually, the point is that I think there was a little error in the presentation, but not in the graph. The graph was done properly, but there is a little problem. I mean, the scaling factor is not exactly the one who is that is in the formula. Actually, we have from the Gamma distribution the peak flow, so the flow corresponding to the 300 years period. Then we assumed that the dynamic of the event or this event, I mean, the behavior of the event, would be compared or similar at least to the behavior of the event of the 1994. So, in order to do that, actually, we computed a number of factors that is exactly equal to the number of points that are plotted in the graph of the orange point. And this factor is given by the ratio between the discharge of the 1994 over the peak discharge of the 1994. In this way, then, the discharge of the event of the corresponding to 300 years period is just given multiplying this factor, they are different, it's not just one, by the peak flow of the 300 years period event. So there was just a little bit of confusion in the presentation, but I can assure that the graph was computed in the proper way, and as I described now, just I think something was difficult to understand maybe, and the presentation was done.
Okay, so the answer has to be, if you want to go on TV again, you need to make short answers. You know, I think it's more clear by the way. I think James was completely lost, even on the topic of the question of the answer. Just for the pleasure, could you come back to the one, I don't remember the number of the slide, I think it's maybe 7, the one when you have the global graph. Okay, 8. What is the blue dot, so which is 300 something?
Is the blue not that?
Yes.
Yeah, this is the observation corresponding to the event of 1994.
This is what I was expecting. So the return period is?
More or less 17 years. More or less. It's 17. It's
I don't read the graph as you read the graph, but it was just.
Yes, it's the logarithmic scale, so it corresponds to 17. It's a logarithmic scale. So, yeah.
No, it was just a comment. So, Elodie has a question.
Okay. Thanks for the presentation, especially in the higher part, because I think it's good to work. And I have one question about fiber, not fiber, but higher parts. Did you model in your in fiber the wears and the dikes? And if not, did you check if the representation of your dikes in the mesh is it well represented or not?
Well, for the model we did on Eber, I just checked because we have them. Yeah, on the upstream part of the river, where the water depth is higher, when we zoom in, we can see more clearly that the water depth corresponds to the an erosion part downstream the weir. Because if we just keep the DM file or even the background map, we can see the wear on the mat and on the DM. So we see the difference of elevation between the upstream part and the downstream part, which was at some point 4 meters of elevation, or on other parts 6 meters. And unfortunately, we didn't have time, but we could have also done a simulation trying to reduce the elevation of the weir in order to see what could happen on the downstream part and see what effects will be provided by deleting the weir. But we didn't have time to model this.
I have a very short question. For your 1994 and for the video, what is your downstream model? Because it seems that you have still little problem. There is some water which is going from the right.
For the downstream, we set water elevation in the sea, which was 0.2 meters, and we checked also with the water flow coming from the river. The water elevation was higher than the downstream boundary condition, so there were no water flowing like inside our model, just going out. But you mean on the right part? Okay, yeah. So this is because our model was wider than the one for the 300-year tutorial, but we created a raster or a false DM to get the elevation in the sea, and the right part of the model is the rest of the DM, which is going up, but the water is just along the coast and not going on the European area or in the airport.
Yeah, from my point of view, I think you've done just a comment, a good work, because it's not easy to set up a proper model for the river. So in 4 days, so I'm surprised that you did a really good job with that. Just
Thank you.
Good. Thank you. We have time for 10 minutes break. Yes. And then it will be the team number 1. We start again at what? 37. Can you take your seat, please? We will start with the team number 1. Where are they?
No computers. There is still some screening. Thank you. Let's go.
So, hello everybody, we are Team 1 and our topic this week was structural measures for flood reduction, management of slope, management of weirs, including weirs removal. So, first of all, we are going to talk about some generatives of the weirs, then about our input hydrograph, and then we're going to show you what we did on AquaCloud and AquaCloud. So first of all, a weir is basically a structure that is built across another channel. So in our case, the Var River, and that changes the water flow characteristic, as you can see on the figure. And it allows to measure the volumetric rate of water flow and store the water upstream. So to recapitulate quickly, we used to have 11 weirs built on the Var from basically the mouth of the river to 2 kilometers upstream of the confluence of the Esson and the Var. And today, weirs 2 and 3 were destroyed during the 1994 events. And we have weir 9 and weir 10 that were decreased by 2 meters a few years ago, and weir 8 should be decreased soon. So the basic effect of a weir when we put one in a channel is that it creates a downstream control, and so the water level upstream is higher. But in reality, it's not really that perfect, because due to the weir, we have a problem of degradation of the riverbed, and the water table is lowered. We also have a problem of selective sediment transport with suspended log between sills, and we have deposits of silt and clay that waterproof the ground of the river, and so the groundwater is not really able to regenerate itself. And finally, we have sedimentation upstream the sill, as you can see on the animation, and we will also have some erosion problem downstream that could lead to a risk of sills collapsing. So in our model, we will use a weir equation with a weir coefficient. And so basically it comes from the direct application of the Bernoulli equation with a few hypotheses. So the streamlines are straight and parallel. We have a uniform velocity. We have horizontal fluid particles when they pass over the weir. We have an atmospheric pressure, and we also neglect the influence of viscosity, turbulence, and surface tension. And so, by a simplification of the Bernoulli equation using the water rate when the flow passes the weir, we are able to isolate the velocity. And by integrating this velocity, we are able to calculate a theoretical discharge. And so in the end, our real coefficient is a discharge coefficient that is a ratio of the actual discharge and the theoretical discharge. And the main difference is that the actual discharge takes into account the errors and the frictions. And so this is this coefficient that is used in the formulas in the software. And in the end, the value of the coefficient will depend on the geometry of the rim.
So let's go to the hydraulic model setup. In the hydraulic model setup, we need a flow hydrograph as upstream boundary condition. And we want to use the Mike Shi results of last week, but we're aware that the results were not very good. So we recalculated the parameters such as the net reform friction and the non-trivial number. And we recalculate the phase flow of each branch. So we obtain our final hydrograph that's shown in the figure, the red line, the red curve. But even though the stimulated peak discharge is almost the same as the observed peak discharge, but it occurs 3 hours earlier than the observed one. So maybe the solution would be to change the network on Mach 11, because as we know, the Mach is a physical distributed model, and it calculated the river flow in the grids from one point to another point. It is a straight line, but in reality, the water flow is a complicated curve. It will take much more time to flow from one point to another point. So we decided to use the hydrograph, simulated hydrograph in HAC HMs, which is considered more pertinent. So in 2D model setup, we would like to use MyFlat. MyFlat is a combination of 1D and 2D model. The 1D model in MyFlat could be Mach 11 or Mach Urban and Mach Mouse. The 2D models in MyFlat could be Mach 21 or Mach 21 again. In our case, we want to use Mach 21 coupled with Mach 11, and we want to obtain flood maps for different scenarios of weirs. The general assumptions in MyFlat is that the fluid is incompressible and homogeneous. The flow is one-dimensional. We consider also uniform velocity and the water level in cross-section. The water slope is small, and also longitude, variation is small. We consider hydrostatic pressure distribution. The most two important equations in MyFlat are continuity equation and the momentum equation. When we set up when we finish my model setup, we found and we run our simulation, but we found the problems in our results. There is not enough water generated at the beginning. And when we check out the water depth result of the field simulation, we found some of the cells were empty. That means that there is not enough water existed that could be transported to the neighbor cells. And also the simulation times is too long because we use 5 by 5 dm level, which is too fine. So we didn't obtain the result we want. But the potential solution could be use 50 by 50 dm or 75 by 75 dm, which will take much less time to simulate. And also we can increase the water inflow at the beginning in my
No, press the button. Just press the button.
Wait.
The red one. Down. Yes.
Wait. So the another potential solution is with that we want to add the water flow at the beginning in Mach 21 to make the water flows in our analyzer domain. But unfortunately, we did not have enough time to do it. But however, even though we don't get the 2D results in MATLAB, but we still have the results in hydroeurope and HECROS, and my different ocean will present.
Okay, so we want to simulate the flood to see the impact of wear and slope during this event. That's why we have chosen to do a simulation on HDRS. So the main principle of HDRS is to represent the fine and geometry of the river thanks to RGS and thanks to DM. And then to run the simulation and the model thanks to AquaCloud, which is a one-hydraulic model based on the one-D shallow water equation, which takes in account constant water level and main value of the velocity for each cross-section. So for that, first we have used DM of 5 by 5 meter from 2013. So we have drawn, as you can see on the two pictures there, first the flow paths and the banks to define the riverbed, and then the floodplain. So then we wanted, our goal was to compare two scenarios. This scenario one with waves and another one without the waves. So for that, we have defined our boundary conditions, which are at the upstream part, the HNS flow hydrograph at normal average, and downstream normal depth. Because our study area is from the rear 10 to the rear 1, but just above. That's why the normal depth is correct for that simulation. And the geometry of the wave is a broad principle. So some parameters of our simulation are written in this table. So we have some differences between the number of cross-section between the two scenarios, and we keep the same interval between two cross-sections and the same many coefficients for the two simulations. So here you can see our profile for the two scenarios. So for the first one, you can see the weirs, and you can see that we have had above the topography, the geometry of the weirs we have built and defined on AquaCloud. So these weirs are added on the topography, because without that we were not able to run the AquaCloud simulation because of the equation. We're not able to take into account a steep variation of the topography. And then with the second scenario, we have decreased some elevation points to smooth the slope and approximate the topography without any work. So these are the results we have obtained with the weirs and the one without the weirs. So for the first one, you can see that we have some flooded areas, the upstream part, and then also near to the weir number 1, close to the airport. And on the second result without the weir, you can see there is a part where you don't see any water, but in fact it is because of the topography we have changed and the geometry because of the point we have decreased on the previous slide. And this is a wrong representation of the reality because, in fact, as you can see on the 3D view, we have water just because of the TM we have used. So, as a quick conclusion for the HGRAS results, we can say that it was quite difficult to represent the slope and the slope without the waves, and also that the floodplain were quite the same with the two scenarios. We obtained some similar floodplains with both of them. So we can say that there is not a huge effect, a huge wear effect on the floodplain with the waves. So then, to conclude our presentation, even if we encountered some problems with micron, we managed to set up and run the model on hydroeurope, and finally we can see that there is not a huge difference between the two floodplains we obtained, but in fact the waves don't have a huge effect during flood events, but they still have some important effect with main main discharge values. And then the thing we were not able to do, but we would like to do, was to test other scenarios with a class, like decrease the age of some weirds and not erase all of them to see some different aspects of the simulation, and also try to set up another MyFlood model with another DM. So here are references, and thank you for your attention.
Is there any question?
Thank you for the very good quality of your presentation. I just have a simple question. You presented both tools you used, so AquaCloud and AquaCloud, and I think you brought up some time for the study and for the presentation. Why did you choose to use two tools, and why did you choose to present both if one didn't work that much?
So we tried to represent the flood event with MyFlood because we thought it was more precise and more correct to represent it in 2D, but finally it was too difficult with the data we used. So then we chose to set up this model with a class of the event simulation. Yeah. First, the goal was to have a very precise simulation, so that's why we have chosen to do that in 2D, but we also wanted some clear results, so we choose just after to do that in AquaCloud.
Okay. Yes. Okay. Any additional questions? No? Okay, then, thank you very much.
Okay, so good day everyone. We're Team 9 and we're going to present our research question for the week, which was representation of river geometry in different models. The general format of the presentation, we're just going to talk a little bit about the question itself, how we identified a way to go about answering the question, and then we'll go through our results in the discussion and eventually a conclusion. So just a little bit more on this research question. The representation of the river geometry is how it will be interpreted in the different modeling approaches. Talking about the different modeling approaches, we chose, well, we went with one-dimensional, quasi-two-dimensional, and a two-dimensional approach. And the models that we used in each of those, you can see up there. So for one-dimensional, we used Hecras and Mike 11. For quasi-2D, we still use Mike 11. And for two-dimensional, it was Iber and Mike 21. To identify the river geometry, it was broken down into three parts. The riverbed, initially, so that's looking at the shape, the overall shape and the length of the river. The hydraulic structures are then found along the river, so in general, weirs and bridges. And then floodplain, and its morphology and its structures, buildings, roads, and so on. The study area that we choose was from the mouth of the Var and about 5 kilometers inland from there.
We started the modeling of the study area with Andy software, across and Mike 11, and I'm going to present possible inputs for each software that can be used to reflect geometry of the river. First of all, we represent the geometry of the river and the floodplain. We extracted geometry from DM in ArcGIS to apply to Hecras, and it can be that the geometry can be seen on the left side of the screen. And to make it possible for 1D model to correctly represent the flooded areas, we place these in the location of riverbanks. And this way we remove the possibility of false floodplain occurrence like it's shown on the left side of the screen. The same was performed for the Mike 11 model, which is also based on the DM that we found for the study area. It's also possible to add wells and bridges in the geometrical representation of the river in both of those models. We tried to add the bridge, and we using the provided toolkit that was in the Hecras, but we found it. But the model we constructed was really unstable, and we weren't able to complete the computation for the model. So we tried another approach, and we modified cross sections to represent the geometry of the hydraulic structures. In Mike 11, it was possible to add wheels, and they are it was accomplished by using a built-in function that uses empirical equation, which is presented on the slide, to calculate the energy loss around the structure. We also played a little bit with adding the representation of the buildings to the floodplain to maybe observe how the flood behaves in 1D modeling. And we can be done in terms of in case of Hecras, it can be done by two ways. We can either modify the cross section cross-section itself, where we can modify the DEM and then modify the DEM with by adding the representation of the buildings, and then after the extraction, they will be represented in the cross-section. And I really did the easiest way to do this was just to modify the cross-section. And we observed that the buildings that were added to the both models, they do not affect the model in the same way that it happens in 2D modeling, but they still have an effect because they are conservation of the mass by taking the space that would be normally occupied by the water. And here are the results of our computation. Is the flooding for the. It's displayed in a true form from across the map graphic. And the same we were able to observe the. Sorry. We are able to observe the overflow, which can be seen on the right side of the slide. The overflow over the banks of the river could be observed in my comment.
So in COSE2D model, we simulated the flood based on 1D model. The difference between 1D model and 2D model, and COSE2D model is that the COSE2D model, we can see the overflow coming from the river or from its upstream. But with the limitation of 1D model, we can only see the overflow from the river. But actually, the overflow comes from its upstream. So COSE2D model is closer to the reality than 1D model. Here is the result in COSE2D model. We used MicroLab to do it. We added another two branches and linked them with the main river. From representation, is the same as 1D model. For HD parameters, we have no time to set the structure coefficient for each branch, so we also have the same as a 1D model. So here for COSE2D model result, we can see that these are overflow zones where the water level passes over the river bank. From these three cross sections, we can see that in the cross section below, the overflow may come from the river at the right of this branch, or it may come from its upstream.
So now we are going to speak about the different possibilities to represent the geometry of the river in the 2D software, so for Hyper and Match. So on the left will be on Hyper and on the right. So for Hyper, it's possible we can draw all the limits of the river bed, and so it's quite an accurate method because we use on the background of the orthophotos of this. So it's an accuracy method to represent the shape and the length of the river. And after this, we can generate the mesh. So we can select the size we want and which kind of structure we want. So we can see the structure mesh for the riverbed and below a structure mesh and structure mesh.
For the mic, this is a river bed we made with mic 21 and mic 21 FM. Mic 21 is structural model and mic 21 is flexing model. So to find out this, we compare two methods with I. And this is constructions in the lower river with the bridges and buildings in the mic 21 and mic 21 FM. For the mic 21 FM, we use use AquaCloud and shapefile here. And on Hyper, we can add some different hydraulic structures, so such as curves, wedges. So, for example, we saw many curves at the top of the part, and below we saw two wedges. So one is number 3, which we can recreate a represent of the shape, the real shape of the number which is arches, different arches. So now it's also possible in Hyper to add the structures on the flood plane. So there are two ways to do this. First, we can draw one by one all of the buildings of the city of Nice, or we can also report shapefile, which is all the buildings are already drawn. And in Antipolis, we draw all the limits of the river, the floodplains. Also, we create an airport area and beach area. We assign all the lines value for each this. And this is my floodplain. My 21 used the same DM. Here we used 20 meter DM here, and my 21 FN. We can use different mesh DM. So in my 21 FN, we can put different mesh size depending on the preference. This is our result of my. This is my 21 and this is my 21 FN.
So in order to summarize, we constructed this small table, which is looking at, for each modeling approach, how a general overview of how the geometry is represented for the river. So for one-dimensional, it's the entry of global coordinates to establish the shape and length of the river, and then the local coordinates for each cross-section. And in terms of hydraulic structures, it varied between Hecras and Mike 11. In the way that in Mike 11 it's not equal with both. In fact, you can add the structures directly to the cross section or add them as features. For reasons of stability in modeling, we varied this between the two modeling approaches, or the two modeling softwares. And then for the floodplain, it's once again the modification of the cross sections. But for the quasi-2D approach, which is basically an upgrade on the one-dimensional approach, the only variations between is with the floodplain and the addition of the flood branches either side of the river that you can see there, and the link channels between the flood branches and the main river channel. And then with the two-dimensional approach, which offers, like I said, the most flexibility, with the riverbed represented with a structured and unstructured mesh, and then the definition of this mesh, and then a modification of the mesh or the DM, depending if it's with Hyper or Mike 21, and the use of the clerical equations as well. And then in terms of the floodplain and the addition of buildings, the use of a shapefile, the modification once again of the mesh to represent the buildings on this floodplain and the other structures. So thank you for your attention. Questions?
Thank you for very nice presentation. I'm just going to appreciate the last slide. I have maybe one question and one remark. Could you please go to the presentation of your result with Mike 21 and Mike 2?
Video.
Because it was very quick and I didn't figure out how, okay, yeah. Here, could you play? So I have to go to my remark. I thought that I saw something straight. Yeah, exactly. What's happening here? Why there is a floating just in the middle of airport? What is water coming from?
With the buildings and bridge, this is because of bridge events, where the water is overflowing. Because of the bridge, there are three bridges we made. The effect of bridge, the water is overflowing.
How the water gets to this part in the middle, like a lake in the airport? Where does the water come? It looks like a completely disconnected.
What is the scale of your white density? What is your color scale for white color?
White color is 0 and 0.09. The last one is 0.
Okay, so that means that you have some water which is already coming and which is white.
Yeah.
So this is maybe join my remark about the quality, visual quality of presentation in the slides. There's plenty of graphs which doesn't have any label, and finally you don't talk when you present it. When you talk, when you discuss, you don't say anything about this. And it's just mysterious lines. I don't know how to interpret. It's strange. And then if you go to the part where you're presenting the mesh, here, for instance here. So what's happening with the visualization of hybrid mesh? It looks very weird to me. It looks like doesn't look like a mesh. It's just, well, it's not a question. I think there is a problem in the resolution, but you shouldn't present such kind of visual support because it's not very. I assume it's triangular mesh. But if I wasn't a modeler, how could I understand this?
If I can give you an answer of sorts for the reason why maybe the presentation doesn't look as good as it should. We did try maybe by that order we could shoot with the number of models that we tried to create for the comparison purposes.
I mean, the issue is in how you present your results.
Oh, I agree.
It's not in the results. It's just.
What I'm saying is in the limited amount of time that we have, maybe the presentation suffered. Is what I'm saying.
I mean, the message is don't try to put so much information.
Yes.
So you can use another graphs, another slide, and so on. But just be sure they are just straightforward and just explaining what you would have demonstrated.
Thank you.
It's clear what Constance said, and so everyone in the room has understood. In that case, you have a 300 mesh just because you have too high resolution for your pictures. That's why we mix and we have just gray lines. But imagine someone else who is not from the field, who is looking at that. Okay, it looks very nice. It's a bit modern art style. It's funny, but it doesn't understand what it means behind it. So you don't produce too much just to overload the things by sure. It's not a, it's just a remark. It's not only for you, but also in some of the presentations. Okay, thank you very much.
So you know the first office that we have I don't know. Where was the copy in documents? Are we going documents? Yes. Big fun. Yes, that way.
Our topic for this week is the resilience estimation for the event 1994 and the uncertainties analyzed. First of all, we split our task into different parts and to make it more efficient. To finish the problem, we follow the process like that. Since we did so many modeling in hydroeurope, so we start this week with the flat map, and then to see the damages. And then we make a study on the resilience concept, and then we evaluate the resilience, and then we did the uncertainties analysis. To start with the flat map.
To start the study of the resilience estimation, we need a fluid map which represents an event. So for our case, we choose a fluid map which represents the 1994 event for the Nice area. And this fluid map, you can see the location on the picture, and it's provided by our tutor.
And then, what is resilience? According to the speech from Jelena Batikov last week, we know that the resilience represents the capacity of an urban system or a community exposed to hazard to adapt by resisting or changing in order to reach an acceptable level of functioning organization or structure. So we think the resilience study is realistic for flat risk management. And so how we evaluate the resilience, we use the flat resilience index. And what is flat resilience index? FRI include two parts. One part is to the building scale, the other part is to the city scale. We can see the two equations for both, and the equations look similar because they all have the same part with the multiplication of the availability and the importance. And there is one chart there showing that from number 0 to 5 shows the availability to 0 to 4, and from number 1 to 5, if the number is lower, which means the importance is lower. And we start with the building scale. To evaluate the resilience of building scale, there are 8 urban functions should be taken into consideration. Here we just give an example of the function of application with the 0.5 meters flat depth. And we can see, we think that the energy, water, and waste and communication is full available after the flood, and the transport is less available. And for the WI shows the weight, which means the importance. So we think the water is the most important, and the less important one is the waste. It's the same as food, occupation, and access. We think food is full available after the flood, and food and access are full available, and for importance, the occupation and access are most important. So after the calculation with the equation before, we get the FRI for building scale is 4.76, and then is the city scale.
For the city scale, we should take into account more indicators. In our case, we have 91 indicators, so we divided them into 5 dimensions with natural, physical, institutional, economic, and social. We calculate the resilience also using the 2 parameters like building scale. building skills, the availability and the importance. For each dimension, we give you just an example. For example, the capacity to avoid the flood, we use the value 3 because during the flood, it is available, but not fully available. But this capacity is very important for prevent the disaster which will happen. So we give the important number value 5. Then the uncertainty is related to resilience. For us, the uncertainty is the evaluation of parameters that touches the resilience in both building and the city scale. We will present it in this. For the flood velocity, because we don't have data about the flood velocity, so we didn't make the analysis. But we can imagine that if the velocity is very high, it will cause more damage. So the resilience will be very low. For the flood death, we give you the example of the in building scale. We can say that in both the graph with the flood depth goes higher, the FRI value is going lower and lower. It is because the flood depth is represent the level of flood. If we have a very big flood, the flood depth will be higher. So it will cause more damage, and as a result, the resilience should be low. For the flood height, we consider 3 flood height. It's coastal, rainfall, and fluvial. And we consider during the flood, we use the same availability for each flood. So it's also the example of the capacity to avoid the flood, which is the value 3. But for each type, we give the different important value for each flood type, and we can see these 2 tables. For example, the natural dimension is more important in the fluvial type than the coastal type, and also we have different FRI value for each flood type. That's the land use impact. We can easily imagine that during the flood, the energy is very important for hospital, but not very important for church. So the land use will have influence for the resilience. If we have the same during the same flood, we have the same flood depth, we have a different resilience.
The flood erosion has also an impact on building scale for the flood resilience index uncertainties. For example, for the same flood type, depth, and land use, the availability, so the R parameter, will be the same for long and short duration. But concerning the importance, it will be higher for long flood duration than short flood duration. The last part of the resilience estimation is the assessment of damages.
It's an important part because it's to help the insurances to know the cost of an event and to in order to compensate the victim. So to do this, to assess the damages, we need the flood map copy with the building shapefile and the date damages curve named TDC. First, after we copying we couple the flood map and the building shapefile. It's possible to know the surface impacted in square meter, and on the graph we can define the cost for each urban function. In blue, it's the curve for the health, in red for housing, and in black for religion. On the vertical axis, it's possible to see the cost, and on the horizontal axis, it's the water depth for the event. So, for example, with a water depth of 0.1 meter, and for the housing urban function, we have a cost estimated at 40 euros per square meter. It's possible to reduce the influence of the food resilience. We have measures like raised house, barriers for the door, and sandbags. So it's these are positive measures, but we can find negative measures like houses with cracks, and this case will have a higher cost for the damages than normal condition. With according to our number that we have assigned for the flood resilience index study, the flood depth is a factor that has at the end the most important impact on the flood resilience. Then it's the land use after the flood duration, and finally it's the flood time.
Questions? Okay, great. You have put something which is dealing with my question. Page 16. You say that the most important factor is flood depth, right? And seeing previous slides, I had a question with this. Might there be some problems with some modeling tools due to this modeling, this flood depth, which is very important? You are saying that the most important part is flood depth. So that means that you should model this flood depth perfectly. So can you have some problem by choosing a bad modeling tool?
Actually, we use full map provided.
I know. But apart using the flood map provided, if you need to do a model and to do simulation, to provide this flood map, and then to get resilience results. So you are saying that flood depth is very important. So there might be, I think,
Well, we tried to focus on the scope of the question, which was more towards the resilience and the uncertainties. I mean, producing a flood map is out of our scope, let's say.
Yeah, so you are not answering my question. So let's go to the slide. I think it's page 10. Okay. Is it the good one? Yeah, you are, maybe not the perfect one, but you are saying things with values which are 0.1 meter, so with some software such as My21, there are parameters called the flood and dry, that's it? Yeah. And by default, the values are 20 centimeters and 30 centimeters. So that means that the criteria that you have 0.1 and 0.2, it shouldn't be well calculated. You got it? No? No. Okay. You have done no modeling?
No, it's not our scope. We wasn't asked.
I'm not so sure because you have not answered to the last part of the question. You have a question dealing also with uncertainties. So,
It's just a remark about the modeling, the 2D modeling, about the flood and dry net. It's just keep in mind when you use a software in 2D modeling, you have this, there's all this flooding depth and wave depth. And if your drying depth is at 0.2, you cannot compute the water depth in the 2D models. So just be careful with that. It's just to make that if you want to model something and to provide a flood map, just keep in mind this flooding depth and drying depth is important in the modelization. Just to mention that. And it is the part of uncertainties when you generate the flood map. Okay? When you just generate
I just like one remark, our scope was not producing a flood map. We did not produce a 3D flood map. I don't know why all the questions are about flood maps. It's not what we were trying
No, I think the question was if you reduce by 10% the extension of the flood map, did you reduce also by 10% the resilience? Or did you increase by 10%? That was the question regarding uncertainty. You know, if you reduce by 10% the water depth, what are the consequences regarding the estimation of the resilience?
That's, I mean, right there you can see.
No.
Remember it's not just not percentage, you can see.
No, it's an estimation for one case. So the question was about uncertainty. If you change the extension of the flooding, if you reduce, if you expand, what's happened regarding resilience estimation? How far it changed? Does it stay the same or do we reduce? Of course, there is threshold effect. Okay, but it was not shown then. Okay, there is a question. Yes, Philippe.
Just a short question. How are you addressing the question of flow velocity regarding the resilience?
I think the flow depth and flow velocity are very related. So once you answer one of them, you're practically answering the other, because they're like they're related to each other. Some
No, like something. For this particular case, they used the flat graph that was given to the students from the tutorial, but they were posting their analysis just on the estimation of resilience. For the flat map, they just had the flat depth, the maximum value of the flat depth, so no velocities. So they mentioned that in the theoretical way that the velocity should be analyzed, but they didn't do that. They just did the flood depth and the different flood types and the different values.
Yeah, but the problem is how you can trust in this flood map.
But this is just a case study.
When it's about the maximum, like it's not about the extent.
I think we were able to do at least one flood map.
We
to deal with advanced increase of players. That was the first part of this assignment.
Okay, good. So at least that will be for the lunch break debate. If you have nothing to talk about, expect the result, and that will be a good topic. Let's thank you. Let's move to the next meeting.
Good morning, everyone. We are team 3, and today, in the last presentation, we are going to answer the question that was required. Our topic is the uncertainties in 1D modeling for the environmental body. Uncertainty is the lack of certainty, a state of having limited knowledge where it is impossible to exactly describe the existing state. We don't have to confuse uncertainty with errors. And also another key point is that models are tools to understand the reality. As we have been told during this week, models represent the reality, but we don't have to lose the we don't have to lose the physical meaning of what we are doing to understand the simplification of the model. And that's why all modeling necessarily involves uncertainty. And it has as engineers who have to decide what degree of uncertainty are we going to admit. The sources of uncertainty could be the data. It's very important the quality of the geometry or topography of the input hydroeurope. And it's very well resumed in this sentence, like rubbish in, rubbish out. Also, the assumption of the model we use could be a source of uncertainties. And also the parameters, for example, the weight coefficient of the roughness is a source of uncertainty, and they are also normally used to calibrate the model. And hydraulic modeling is a technical process consisting in reproducing free surface flow dynamics using physical and mathematical models. In 1D models, the flow follows a predetermined path, and velocity is averaged across the in each node. 1D solution of the water shallow equations are based in these assumptions. The velocity is uniform across the cross-section. Water level across the section is horizontal. The vertical acceleration are negligible. The channel slope is small, and resistance load to represent the boundary friction and turbulence. Our goal of the 1D model is to locate the potential sources of fluid. We have done the model in aircraft, and we have also done sensitivity analysis of the different sources of uncertainty, so we can know the degree of uncertainty. And now my colleagues will go deeply on this.
So for the data, we have input hydroeurope, geometry, and sphere level. We will begin to start with the input hydroeurope. So it's important to mention that a part of the statistics is related to the observed hydroeurope, and usually the values of what is charged are given thanks to the rating curve, which represents the relation between the water level and the discharge, and it is established on the same cross section. And here I will explain these 5 sources of uncertainties which can affect the accuracy of the result. The first one is uncertainty in river discharge measurements. For example, we can mention the influence of the wind and also the gauging uncertainty. And secondly, we have a rating curve uncertainty. You can see here in the graphic that we have only few measurements are done for long water depth, but and we have to interpolate and extrapolate to give the other possible value for the discharge. And third, we have uncertainty induced by the presence of uncertainty flow condition, and in case of uncertainty flow condition, 2 units are added to complete the rating curve. The higher one for the increasing part of the hydrograph, and the other one for the decreasing part of the hydrograph. And the fourth one is uncertainty induced by seasonal changes in the of the river roughness. And here the rating curve is different on different seasons because of the variation of vegetation in the riverbed. And finally, we have uncertainty induced by changing the riverbed shape, and it means that the riverbed movement should be considered.
Moving on from the theoretical part that my colleagues discussed, now the way that we are trying to present the results to you in terms of numerical figures and also by graphical representations is by following few steps. And our first approach was to do some modifications to some artificial modifications to this hydrograph that we used. Here we used the 2011 event, and then what we did was we wanted to investigate what will happen to our results if we do some modifications to our hydrographs. For this case, what we did was we increased the total flow by a value of 20%, and also decreased the total flow by a value of 20%, and then we investigated how the final representation of the flood will look like numerically and also graphically. From here you can see the model also responds correspondingly according to the increments and also the decrease. And we see a small difference in the stage that we observe at the cross section, which is recorded at the Napoleon Bridge Street, which is just 1.34 meters when we decrease the value, and also 1.56 when we increase the value. And these are the numbers, and we want to see how the flood extent also, not really flood extent, I mean how the areas that are possible to flooding, because we use here only one piece model. So here we can see according to the changes that we imposed, we can see that clearly, visually, we can see that there are differences in the places where the flood is occurring. And moving on from there, the next element that we wanted to check was the geometry. So now we know, since we use HECRAS, we wanted to digitize the geometry by ourselves, and then for that we use HECGeoRAS program. And here, usually the cross sections are defined according to the preference of the model. So we wanted to investigate what happens if we keep the cross sections very closer, and also what happens if we leave out some space in between the cross sections. So this was basically done by using by 3 different steps of using different cross sections intervals, which are 250, 500, and 750 meters. So as we can see from the results, also here we can see a clear difference, which can pose an uncertainty, because 250 to 500 meters, we might not really notice that while working on a very big scale. For example, when we are working on a computer, the difference might not be very visibly visual for the model. So this could cause a huge uncertainty also to our results, to the result that we generate finally. And we wanted to see some of the numerical figures as well, which corresponds to each of those differences. The first three graphs shows the observed stage and the flow graphs, which is recorded at the cross section near the Napoleon Bridge. One thing we want to point out is not exactly looking at the numerical figures, but what we wanted to point out was that when we kept the cross sections really close, we observed some instability at the beginning part of the simulation. So it might be like an obvious thing that when we keep the cross sections, the interpolation will be quite accurate, but we have to notice that keeping the cross sections quite small also could result in some problems. And we can see that numerical instability is disappearing as we increase the distance between the cross sections. However, we increase it further up to 1 kilometer as well. And this could, again, I mean, we cannot keep increasing the cross sections as well, because when we increase it to 1 kilometer, the model did not simply run because it was just too far from each other. And the figure down below, you can see the flow differences which was imposed by each of these different changes. And as you can see, there was the highest difference of 84 cubic meters was recorded when the cross section was kept at 250 meters. And the next thing that we wanted to investigate was a source of uncertainty was by using different types of DEM with different resolutions. And as we did our default simulation with a 5-meter resolution DEM, and when we move from 5 meters to 30 meters without changing anything in Hector's interface, just by changing the DEM, we can see that still it has a small inverse, but not as much as what we observed in the previous one. Numerically, we can, as a numerical figure, we can say that we observed a difference of flow of around 14 cubic meters at this specified date. And the next parameter we wanted to investigate was the influence of the sea level. Now, from literature, unfortunately, we failed to mention the reference here. We decided to use a sea level of 0.45 meters as our base simulation, and from there we also wanted to check how much our result could influence depending on the differences of the sea level. And this we observed that the uncertainties that could be imposed by such small amount of changes in the sea level is quite low, relatively. As you can see, we see a difference only in the beginning part of the simulation, but as we move along to the other parts of the simulation, we don't quite see a difference in our results. And from here on, my colleague will talk about the uncertainties that also could be imposed by things like roughness and also the wave conditions.
Okay, so we are coming to the final category of uncertainties. So the source are the parameters, and in our model in Hector's, we had to apply two values of parameters, so the roughness and weirs. The first one is roughness. I'm sure everybody knows this equation by now. So this is represented by magnitude emissions, and its general meaning is to represent the overall flow resistance. The uncertainties come from several aspects. We can talk about the method of selecting the manic value. It is usually selected from typical values given in tables, which is obviously also an uncertainty because the real riverbed is difficult to assign to specified categories. The vegetation changes in seasons, in months. It can be washed away by floods, or it can flourish, and it has a great influence on the roughness. The sugars and riprap extraction is about the dilapidation of embankments. So if they get destroyed, the surface is changing, which means that the roughness is changing as well. The 1D model approximates areas between cross sections, which means that the parameters should be representative for the whole segment, which is even harder to achieve. And in reality, the roughness depends on discharge, so it's not really a constant because discharge can cause some difference, some changes within the riverbed. For example, wash away vegetation or sediment, or on the contrary, carry debris that may clog the riverbeds. So that's for the theory. The estimation of importance of the uncertainties is once again presented by a graph and a table. So we have a sensitivity analysis. It basically shows that we definitely can't neglect the effect of changes of roughness within the range that we have chosen. It's quite significant for the elevation at Napoleon, and as well, it is visible when we compare the visual results. So the general flood sources of flood areas are the same. There's a downstream and upstream area, but you can clearly see an increase in potential flood terrains with the increase of roughness. And it applies both to the downstream and upstream areas. The wind coefficient, once again, this equation should be familiar for you. The coefficients, regardless of the type of the weir, the AquaCloud uses the same equations. And once again, there are several sources of uncertainty for the weirs. It's usually based on typical values, once again. The hydraulic characteristic of the weir by changing time is caused by sediments filling ponds and downstream erosion or general dilation. The actual shape is irregular. I'm referring especially to the weir downstream from the mountain bridge. In reality, C is once again it's not a constant, it's dependent on the discharge. And although referring to the 94 flood events, it is very difficult to model weir distraction. For the estimation of importance, this time, because the effect on the downstream area was very little, we used a different cross-section, directly downstream of weirs, and there the difference was, we could say, significant, but further downstream, we could not see any differences in potential flooded areas. So we decided that this sensitivity analysis suggests it's not a important question.
So, in the function of the sources of the flood, we have decided to divide the lower bar valley into two parts. The first part is the upstream and the downstream, when we can observe an overtaking, and in the middle part of the river, the sources of fluid can be produced by a sewage system. And as we have before, we have three sources of uncertainties. The uncertainties on the model, data, and geometry. The first one for the model, we have chosen to use AquaRust as one model, and we know that the one model is valid for the to quickly predict the potential initial point of the incoming inundation, but we have some limitation in the 1D model. For example, no information of the fluid tank and one direction of the fluid. And for the data and geometry analysis uncertainty, we have established a table with three colors. For example, for the low importance of uncertainties, we have Wells coefficient, sea level. For the medium importance uncertainties, we have selected cross-section interpolation and DAM, and for higher importance uncertainty, we have input hydroeurope and roughness. So thanks for your listening.
Question because we talk about uncertainties. So I do not see your conclusion. How can you solve this problem, or what's the solution for these uncertainties? Because we explain what is uncertainty in this old slide, but what's the solution?
Yeah, it's a question that also we had. I mean, we did not really go into that, but we can always, by looking at this, the results that was produced for each of the cases, we can see that the conclusion that we can draw is from the last table that we presented. We can have a look at the most influential kind of aspects. I mean, most influential kind of elements that could cause a very high uncertainty. And the final conclusion that we can say is that when we obtain these data, we have to be more careful, especially when we go to that side, especially when we get the input hydrographs and also the distance. It's not necessary to be as aware of, as much as aware of when we go to the lower part, because it creates the less amount of uncertainty relative to the higher parts. So this is what
cross-section interpretation is more to that. Because we know that in DER you have some uncertainties, but you just show us that you draw the cross-section with different distance. Okay, but we didn't show the DER necessarily. The shape of the cross-section has uncertainty. Because you can control by yourself by deciding every 1 meter I draw one cross-section, but the uncertainty is not. It's not from how many cross-sections you draw, it's from the DER. You know what I mean?
Yes. Okay, another quick one.
So I think it's my question joins the discussion you started. I really appreciate the talk, and especially the first slide, when you say that uncertainty is not equal error. So what is the definition of both of those terms, and what's the difference? Well, my feeling is that finally he was mostly talking about errors and not uncertainty. But your starting point was absolutely correct, yeah. So do you have any comments on that?
An error, you can measure it, and uncertainty, maybe you can have you can make as well as one sensitivity analysis, but you can measure and you can control the uncertainties. When you do modelization,
we have the same notion of error. I mean, when you're choosing one cross-section or set of cross-section over the other one, it's your choice, and you're choosing to make bigger or smaller error. So this is my, it's not the definition of error, but people understand.
Maybe I just want to add something. I didn't do my notes from here because what I think you did indirectly with your tables where you set percentages plus minus, because I think the uncertainties, okay, errors, uncertainties may be a range of the solution. So your question about what a solution, there is no solution for sure. So the question was, at this point of view, not, let's say, clear enough, because the outcome of you is not to say, okay, I have a solution for uncertainty. That's for sure not possible. The outcome is that we have a range of results which might be possible due to the uncertainties. And this was given in the tables with plus minus percentage. So the conclusion is now, of course, if you give for everybody a result, not say the answer is 17. Well, it's maybe 17 plus minus in this kind of range to take care about this. Yeah, so I think it's not a question of definition, it's a question of how to sell the results. Because everybody wants to get from us an engineer clear, should I have done or not, but we can't give this.
Thank you very much.
Hello everyone, we are Team 7. Today we are going to present about our second topic, which is impact and consequences of numerical method on hydrological and hydraulic model. Let's start. So we focused on these objectives to answer the question of this week. It is to find the fundamental theories behind the interface of the models. And it is to find the impacts of the numerical method, which is used in different software. And also, it is to understand the consequences of the numerical method when choosing a software. And it is to run the model to see the results of either HECRAS and data development. So numerical methods are divided into three methods, which is finite volumes, finite differences, and finite elements method. We work on either for finite volume method and HECRAS, IC, and HEC-HMS for finite difference method. Before start this part, we would like to refresh some concepts. What is numerical method? It is mathematical tool designed to solve numerical problems. It splits the domain into a mesh and then uses scheme to criticize the governing equation over the mesh.
For finite elements method, the core idea is to divide the whole system into small parts to simplify the question. And the finite difference method the derivatives in the partial differential equation are approximated by linear combinations of function value and the grade points. And the final one is the finite volume method. In this method, we divide the whole system into different volumes. Tell the equations. Move on this page is the properties of finite difference method and finite volume method. You can see from this page there are some a lot of advantages of finite volume method. Most obvious one is finite volume method has excellent conservative property. So finite volume method is used most widely nowadays.
So, as most of you may know, we also use with the numerical methods, we use schemes and yes. So the most common schemes are explicit scheme and implicit scheme. So there are here graphs to let you see how it look like. And there are some others that are more complex or more that fits better problem. So brief comparison between explicit scheme and implicit scheme. So the explicit scheme is using quantities at the previous time step. So those are quantities we know. So it's also conditionally stable, while implicit scheme is unconditionally stable and allow the use of long time step values. For the explicit scheme, there is a condition to respect to avoid instabilities. If we use big time step, we are gonna have instabilities. Also, explicit scheme is more easy to adapt to graphic processor units and implicit scheme is more need more computational effort in each substitution step. Explicit scheme has been more used than in the last years. The use of finite volumes has become more popular, and it's solved by the explicit scheme. And the implicit scheme is more complex to program. So as a conclusion for this part, an implicit solution is more stable than an explicit solution, and longer time step can be used. An explicit solution is simpler to program. There is also a notion that I have not talked about yet. It's the order of the scheme. Most of the time we are using low order schemes that are stable but quite dissipative around the discontinuities. We can use high order schemes. There are models that allow to use high order schemes, but if it is in some cases more accurate, it shows oscillation and instabilities around discontinuities.
Naturally, we have two models, two hydrological models with different micromaster valuing the model simulation. And also these two models, HyperMax and MapSheet, applies the Antipolis method to calculate the water movement in the model. And but in the HyperMax model, it's like the routing method. The routing method was implemented by explicit scheme, but in the MapSheet, the implicit scheme was the mathematical scheme with applied in the model calculation.
So concerning the algorithm part, we have used two codes, AquaCloud and Uber. AquaCloud uses a high difference numerical scheme, and Uber a high numerical scheme. And for the scheme is also different. The AquaCloud software uses an implicit scheme, and Uber uses an explicit scheme. The raw first order scheme, so it's more complex than other software, because it's based on the linearization. And both numerical methods solve the shallow water equation, the 2D shallow water equation. So we have also simulated the flood events of November 1, 2094 as the next extra task. And we have to fulfill our role of modeling. So we have set up GN, digital elevation model, properly without bridges, because if we take into account bridges in the other software, the software will consider the bridge as a word. And another important thing is that we have imported a building shapefile, and we have considered buildings as holes. Why holes? The first thing is that if we consider building as holes, the flow depth in the streets between the buildings will be well represented. And the other thing is that some of the software uses another method. They elevate the digital elevation model to represent the building as a volume with a vertical slope. And sometimes there are also buildings with inclined slope. So if the method of representing building as holes is more close to the reality. And
here we try to do 2D simulation with the grass, starting from the data which we get from 12 subclass with the heavy HMS. Here we start from the initial name which we have, and then we try to define our 2D flow area, and then we try to build up our mesh. And we see if there is any obstruction in along the river, like bridge or piers, we can remove the bridge, but we don't have more time, we can remove it. And then we define our upstream volume condition line and downstream condition line. And we enter our anesthetic flow data starting from hydrology parameter, hydrograph, and discharge in the river, and hydraulic parameter, topography and value. Then we run the program. Here we can find the situation of the flooding on the river. We can find here the center of this, the peak of the flooding time. I can show you something here. With the sun. See here, we try to, because the 2D simulation doesn't give us to imagine of the elevation, so this is water surface elevation with the 1D simulation of the grass. And also this speed, the velocity, now between 1 and 3 meters per second. The changing from the center of the channel and the right side and the left side.
So after discussing the methods and models, we'll come back to our question: what is the impact and consequence of these numerical methods on the hydrological and hydraulic models? And since there are so many models and each method may have several different impacts on each method, so we summarize 4 aspects of all possible impacts. Stability, which is the property of the numerical scheme to produce results within the bounds or the range of the initial and boundary conditions. And accuracy, which is the ability of a numerical scheme to produce results as close as possible to the observed data. And consistency is the property of the numerical scheme to reduce its truncation error when the discretization step tends to 0. And the final one is the computational cost, which is the effort we need to complete the simulation, such as time and investment.
I will continue with the consequences that we have there when using the hydrological and hydraulic codes. The main consequences is that numerical methods always will approximate reality, and which won't be as great as the observed method. Also, no matter how good is the code, if we don't use it in a proper way, inaccurate results will be obtained. And it happened to us last week that we completed the hydrograph with Mindsheet. And so it can be a waste of resource in this sense. And finally, in particular for the hydraulic codes that we have used, and regarding the impact, AquaCloud 2D, using the fine difference method and with an implicit scheme, and a larger time step, has a lower computational cost than either using finite volume method with a specific scheme, because, as Jeremy has said, the specific scheme needs a small time step to keep the stability in the results.
After all, we concluded that numerical methods are mainly used for complex problems which don't have analytical solution and are time consuming. What's also important that there is no one best numerical method, and it depends on type of problem to solve and also available data. For your attention.
Any questions? Quick one.
So the question is compare the numerical method with that. So first I would like to ask, can you compare the different numerical methods in the same model? Because in some of the model you have a chance to change the numerical method. Have you?
The fact is that in 4 days we won't have the time to be sure that we will be able to compare exactly the models, and it has already asked us a lot of time to set up the higher model and class model, so we didn't have the time to do those things.
Okay, so and go back for your conclusion. So there's no better numerical method, depends on the problem that need to be solved. Okay, so in this part, which numerical method and model you think is the best?
As we were saying, there is not
compare a lot of models and which model gives you the reasonable result.
I didn't get the answer.
It depends on what you are looking for. If you are in a university of the results or in a computational time, and if you want to have quick results,
which one close to the observed data?
If you want to compute quickly, it's better the different method because it has a less instant, no computational cost. If you want to foresee, it's better than the implicit scheme or the volume.
Next one.
I think the conclusion that implicit scheme is faster, it's in contradiction with what you were presenting when you were speaking on the law. Okay, so could you, so I have another question. Hyper allows you to have different cell size in different domains of the different parts of the simulation domain. Have you used the uniform mesh either or?
No, I use different type of mesh.
So I have a question with respect to C-flat condition. It seems like, so more or less, probably more than a remark, which what I'd like to make, is that the C-field condition for explicit scheme is driven by the smallest cell. Okay? So actually your time step is maybe very low because you're using small cells in some region. This is maybe a reason to use implicit scheme while you're using a different mesh size. So
yeah, but I'm very well use an explicit scheme, you know? So
maybe it's a wrong choice. It's not. It's maybe your good conclusion to say so. We have a long simulation
and we have not finished the simulation. It lasted 15 hours and it's still running. That's why you see the airport is not flooded. And I forgot to say that in the presentation. Yeah.
Yes,
the thing is that it's hard to make final conclusion because, I mean, if you're working 1 month, you will be sure each scheme is better than another, you know, but in 4 days, arrive to different conclusion about this complicated topic. I think.
I understand the time is quite limited, but we are engineers, we should give the solution. Or just like we
it's the subject, because they are subject to the way they are working here. No, just
Okay. I think we will stop for this morning and then move for the break. Sandwiches are ready. We start again at 1:30.